since I've been here. It's great to be back. It's always one of my favorite conferences. Since I was last here, joined ThoughtWorks team in Johannesburg. I'm now in, as Patrick Vine said, I'm now in management. I did issue one pull request to a team, and it was rejected. It was Python code. So I blame it on Python. Since then, I've got a few more opinions. Angular 1 versus Angular JS 2. Like, nah, who cares? Solid, yeah, who cares? You'll see the trend, right? I'm getting a bit grumpy in my age, right? So craftsmanship, like, let's move on. Okay, but there's one thing I hear often, right? And I think which is really, really difficult. And that's DevOps. And then I ask people, why are you doing DevOps? And it says, because microservices, right? And they're like, no, that can't be it. And then I speak to the microservices guys and say, why are you doing microservices? Oh, because DevOps, right? So anyway, that's an infinite loop there, so we'll deal with that. This talk is not a compiler class. It's actually a flight path over external DSLs. Many of us have written internal DSLs with Ruby, many other languages. Who's written an internal DSL? I know we all use it with like active record and RSpec and all of those things, right? There's a beauty attached to DSLs. And in the last few years, I've attempted many external DSLs for various reasons, mostly to come up with a semantic model that's meaningful for the domain. And it's not about the cuteness of it. So this is about that, right? And I'm going to try to do it in 20 minutes. So we are going to use compiler vocabulary. Don't get freaked out. I'm going to try to make it as accessible as possible. You'll give me feedback whether I was successful in that. So what's our flight path? We've got code, like print line hello. How does it end up producing output? It goes into what we call a lexer. Some people call it a scanner. That produces tokens. It just basically chunks it up, and you get each part, right? You pass that into a parser, and then you get an abstract syntax tree, basically nodes, dumb things. You pass that into an interpreter, and you could get objects out if it's an object-oriented thingy, right? And eventually it's passed on to the runtime, and you'll get this output. So there's actually 4 parts. 1, 2, 3, 4. So that's the parts that we actually want to cover in 20 minutes. So technically, the 20 minutes starts now. Okay? And like football, if there's pauses in between because of injuries, we'll add time on. Okay. So here's our domain-specific language. It's for a washing machine, and all languages need to be cool name. Mine's called WML. And you can see there's on stop, then shut down. If the state is ready, then if it gets a start signal, then lock the door, and then tell it to go full water, and you go on and on and on. Nothing dramatic. The nice thing about coming up with an external DSL is that you can take a piece of paper or whiteboard, you can imagine anything and write it down, and it seems cool until you get to actually designing the grammar, etc. But you have complete freedom to come up with a syntax, a structure that makes sense for you to work with. However, you do need a semantic model. And in this case here, I've got types. I just happen to call it types. We could have called it anything we like. In my head, I have types. There's a state type, like @ready. There's an event type, which tells me I should listen for something as a washing machine. And there's a signal type, which tells the machine to do something. Then I also have what I've called blocks. I've got an event block on something. When something happens in the washing machine, do something with it. And then I've got a state block, which says the washing machine happens to be in this particular state. It's either on, or it's off, or it's filling water, or it's doing a rinse, whatever it may be. Then the last aspect to my semantic model is that I have instructions. I can send a signal to the washing machine to do something, and I can tell the washing machine to change state. That's the sum total of my language. Okay. So, given that first step, Alexa, chopping this thing up, what we want to do is scan for types, blocks, instructions, and output an array of tuples. Chunk it up. This is not hard. We parse strings every day of our life. What we actually want to do is scan that DSL code and pick out the parts and store the parts independently. So let's start with on. If I detect on, I want a tuple pair, on and on. Find start, oh, that's an event type. And what's its value? Start. In this case here, I've detected an indent, so I've marked I have an indent. Then I've got another instruction called send, followed by a signal type. And I just walk through the string and just tokenize everything, including the outdent. Now, what do I need to be able to do this? There's tools. Guys have been through comp-sci classes, etc., and they told you about this lex and flex thing, right? You could do that, nothing wrong with that. Recently, or later, there was a tool set called Ragel, which does basically the same thing. In Ruby, there's Rexical. I think it's by Tenderlove. It's pretty cool, simple enough to use. Or you could roll your own for the absolute simplest DSLs. You can imagine what that looks like if you had to roll your own. It's like read the string, chunk it up into lines, chunk it up into whatever your delimiters are, spaces, whatever it is, and just walk it and build up that array. Okay? But there's three things I have found when building up DSLs. Firstly, ensure that it is backed by a consistent semantic model. Don't break your model. You break your model, you'll hurt yourself, right? Second thing is that whenever I've tried to be really cute and fancy with syntactic sugar, it's hurt me. I've overcompensated in my parsing, etc., for syntactic sugarness. So I'd rather give up syntactic sugar for simplicity and correctness of the semantic model. The last thing is that the last stage where I talked about the runtime, how will this thing play out in the runtime? It feels far down the pipeline of building an external DSL, but I use that as feedback to say, how could I simplify this grammar? How could I simplify this language? So we have DSL code, which goes into Alexa, which produces tokens. What we're after is actually an abstract syntax tree, which is that stage at the top, step 2. For that, we'll use a parser. We've got two different worlds here, right? We've got one world, which is tokens in an array, a list. And then we want a thing called an abstract syntax tree, which is a tree-type structure with nodes in them. I've had tuples, I want to make nodes. I've got a list, I want to make a tree. How do we go about doing that? How do I firstly take tuples as tokens and make nodes? The way we do that is that we introduce node definitions, and that's the thing we write. And we'll talk about that in the next slide or two. It's not good enough, though. We parsed that DSL quite dumbly. We didn't care about its structural correctness. So we need to introduce some rules to say this is syntactically correct. And that's what we use a grammar for. And that is something that we write as well. Now, in order to build these parsers are pretty damn complex. When you start looking at structure, correctness, recursive references, etc., it becomes very, very complex. And so we rather opt to pick a tool. And that's called a parser generator. So we feed our grammar into a parser generator, and it generates our parser for us. So we don't write, well, you can write parser generators if that's your job, right? But I wouldn't recommend writing a parser by hand. You could do it for fun or to get credits at university. That's fine as well. So let's talk about node definitions. The first part that allows us to map tokens to nodes. In Rubyland, very simply, I could just need a container to hold all of these things. I'm just using something that's inherited from struct. Back to my semantic model. How do I represent a type as a node? In this case here, I'm just using a struct because they're pretty stupid things, nodes. They've got no behavior. They're carrying data. That's all. So I can use a struct. And I know that struct for types all just take a single value. What's the value of it? Is it locked doors? Is it full water? Whatever it may be. So I can just create subtypes of that struct and use that. And I do the same thing for blocks. The same thing for instructions. And you'll notice that my nodes are actually pretty simple things. There's nothing complex about them. All they're going to do is hold values for me, right? And whenever I parse and translate these things, I'm going to plonk it into that node structure at the top. That's all. Now we need to focus on the parser generator. So we've found a mechanism to create holders for these tokens. We haven't done the translation yet. We're just preparing for it. There's tools for these. You've seen Yak and Bison before in your life. In Ruby, there's rack. So who's used tree tops or pegs in their life? Yeah. So you could use things like that as well. Nothing wrong with that. We're going to use rack in this case, but don't roll your own. Don't. It's complex. Okay. It's hard to roll your own. Well, I shouldn't be that prescriptive and say don't. You can, but just you could get cut. The interesting thing about this is that they all offer a DSL to describe grammars. So we're going to use the grammar DSL to specify the grammar of our DSL. Okay? So it offers us a language that allows us to declare what our language rules are. There's an example, and this is the part that trips most people up. Here's an example. Let's just say you've got some string.split, and this is an example of the rule. On the one side, you've got call, that's the rule. On the other side, where the curly braces are, it tells you what it should do with that rule. So I've got call, and it maps to invoke it. Call is the name of the rule. Invoke it is the name of the node in the node definition. And you'll see that invoke it takes val1, val2, val1, val3, val5. Where do those come from? Well, the rule itself, the first item in the rule, here it's called expression, is val1, and we pass it in. The next one is a dot. We don't care about it. Val3, we are interested in that. That's the one that's called split in this case. And we're interested in that. We don't care about the parentheses. We're interested in the argument list. In this case, it's a comma. And we pass that in. And we don't care about the rest. So you could actually go through and build an entire grammar using that kind of syntax. I'm not going to go through details, but typically with rack, this is what you have. Some segment or section or block that declares all your tokens. You could set up an operator precedence table if you want. And then you declare all your rules. And in this case here, what this says is that my program either does nothing, it's empty, or it's expressions. And what are expressions? Expressions are what's described later on. And an expression consists of an expression. And what's an expression? It's type, send, etc. And what is send, send type. And that maps back to the tokens. Okay. So that's setting up your grammar. By far, it is the most complex part. If you get past describing your grammar, you're good. Make the effort, push through, you get there. So now we've been able to build a grammar that gives us structural correctness, all the rules, the node definitions to map over, tokens. What we're aiming here is for simplicity, keep it small, avoid the sugar, hop between the grammar and the node definitions frequently. It'll help you resolve any tension you find in them. Then we need to actually create the parser. With rack, it's a shell command, it's a gem, install the gem, run rack against your grammar files. Historically, it's .y that comes from Flex and Bison and all those things. And it generates this file for you. And all you need to do is tie your lexer to your parser, which is the code that's right at the bottom. Tokenize the code and then do parse. This boilerplate tying of things couldn't go into your grammar file. There's blocks for actually specifying, include this as the tail end. The things for require Lexa, require nodes are things you can specify in your grammar file to say include this at the header. It's actually pretty straightforward. But here's the thing, the AST is completely dumb. It cannot be executed, it is structurally correct, and it encodes your semantic model. You can't do much with it. It just exists. And understand what we said when we designed those nodes, right? They're completely dumb. They're just carriers of data. So I'm going to jump ahead to the runtime. I'm going to skip the interpreter for a while. You've got at least 5 options. And some of them you'll recognize as programming paradigms. There's procedural, like C-style. There's class-based, which is like Ruby. There's prototype-based, which is like JavaScript, which is by far one of the simplest runtime models to create. I don't know why JavaScript is the only one that made it through. But anyway, we'll talk over that over beers. There's functional, which you know about, like Haskell and others, Clojure. Or you could make your own based on your own semantics. Let's say you want a stack-based machine. You could create your own. There's nothing hard with that either. There's 3 things to worry about here: speed, flexibility, and memory. And they're always in conflict. It's not unique to creating DSLs, it's unique to all of the code we write. Speed, flexibility, memory. That's just it. That's our life. We're also in conflict with this. So live with it, choose the one, play with 1 or 2, compromise on the 3rd, and make sure it's good enough. Alternatively, you might be given a runtime. For example, it might be an embedded controller. I know Lance is doing some IoT thing later on in the week. It's that kind of stuff. You might be given a runtime, work with the runtime. So we've got Lexa and Parser, which produce nodes, and we've got this runtime. The problem here is that it's an absolute collision of 2 different worlds. The semantic model we've had in our head does not match the runtime model. It absolutely does not. So we need to resolve this. So it's the semantic model represented as an AST, and it clashes with whatever runtime model you've chosen. How do we solve that? And that's a mental hack: be the machine. Just be the machine. Think like your runtime. Immerse yourself into it. Get into that state of Zen. Be the machine. And then we'll come to it, but you'll need an interpreter to be the machine. Here's an example of something that's a class-based model, right? The key thing here is that you're actually in meta-programming world. This is what you are doing. You're meta-programming. It's worse than that. You're in meta-programming because you're actually building the meta model. So you're doing meta-programming, okay? In a case like this, we can have a meta object that holds a reference to a meta class, which holds reference to a collection of meta methods. At the end of the day, we're only interested in something that says, evaluate this body with these parameters. That at body you see at the bottom, that's actually your node. Do something with the node in your runtime. This is a very, very dumbed down, trivial explanation of an evaluation of a runtime. So remember our parser? It created a variety of nodes. Remember our runtime? It executed that body.eval. And so we have an interpreter, the thing that helps you be the machine. In our case, all it does is evaluate whatever came out of the AST. And remember our nodes? We're dumb. Now is our time to actually make it work in the interpreter. It had no behavior. In Ruby, just reopen those node classes, and its eval method do what you want it to do. Give it its behavior then. It was to write something to a port, let it write to a port. It was to wait for an input asynchronously, let it wait. If it was to print something to a console, print something to a console. Do whatever you wanted to do. Then we're done. But we haven't got byte-code. So, we want byte-code. This was our flight path. You've seen it before. The thing that we only need to change is that interpreter if we want byte-code. And that's what we do. Between the parser and the runtime, stick in a compiler and a virtual machine. Your compiler, all it does is takes that AST and generates bytes instructions for you, which is then interpreted or handled by the VM, which is ultimately your runtime. Do you want to do this? If you need performance, if your trajectory is towards a general purpose language, if it's for credits at university, or for fun, okay? But you don't really want to build a VM. For kind of work that we do, we don't generally want to build a VM. So what we're after is that rather compile to an existing VM, whether it's a Java virtual machine, the CLR on the .NET, even the Ruby virtual machine, if you understand that and you open up how it works, do that. Even the JavaScript runtime, rather compile to that. So there's tools to do this. There's traditionally LLVM, and someone's got C extension gems for Ruby for LLVM, and you can use that as well. But it is absolutely complex, right? So there's a really good thing that's happening here with your external DSL. We've got code that comes in. It goes through these 4 phases. It's a clash of 2 worlds between the Alexa and a parser, which is ASTs, and your runtime. But aside from those 2 highlighted blocks, you can opt not to interpret. You could have a compiler plus a VM, or you could have an absolute translator. For example, spew out JavaScript if you wanted, and do that. Or some kind of assembly, or some other thing, Lua. I don't know. Generate something if you want. Generate documentation for IK, right? Maybe update Jira. You could do that, okay? Okay, who uses Jira? Okay, keep your hands up. How many of you have a company that uses Jira and you don't use Jira? How many have written a chat bot for Jira, for Slack? Does it move your cards, even if, like, cron job just move cards? Wilhelm? Okay, so that's it. So what we're after here, this is your flight path, 20 minutes from imagining a DSL, pushing it through Alexa to come up with tokens, passing those tokens onto a parser with your grammar, and then there's 3 different paths you can take at least, ends up with a runtime that gives you your output. So, keep the semantic model consistent, keep your grammar simple. Metalan, be the machine. Understand your runtime, then you can map between the 2, right? And that's management of the collision. That's it. That's external DSLs. The tooling exists in Ruby if you want to do that. It's not complicated, it's just unfamiliar. The hardest thing is coming up with the grammar rules. That is what tripped us up most of the time. And then that's it. Thank you very much. How's that? 20 minutes?